Picture a time so far back that even the concept of time feels meaningless, a universe so young. It was nothing but darkness and chaos. Out of that primordial void, something extraordinary happened. The first stars flickered to life. These weren't just any stars, they were cosmic titans blazing with unimaginable power, and their birth set in motion everything that would follow: galaxies, planets, even us. But here's the thing, we still don't fully understand how they formed or what secrets they took with them when they vanished. That's where the mystery gets truly fascinating. What if I told you some of these ancient giants might have been thousands of times more massive than our Sun? Or that their explosive deaths could have created the very building blocks of life itself? For decades, scientists have pieced together clues from the farthest edges of the cosmos, and what they've uncovered is a web of theories so wild, so mind-bending, they'll make you question everything you thought you knew about the universe's beginnings. Some suggest these stars were unlike anything we see today, monsters of pure energy that burned bright and died young. Others believe their remnants might still be lurking in the shadows of space, hidden in plain sight. That's why we're diving deep into 30 of the most astonishing theories about the universe's first stars. From the bizarre conditions that birthed them to their lasting legacy woven into the fabric of reality, we'll explore how these celestial pioneers shaped the cosmos and how their echoes might still influence us billions of years later. So buckle up, this isn't just a journey through space, it's a trip back to the very dawn of existence, where the rules of physics as we know them were still being written. By the time we're done, you'll never look at the night sky the same way again. Imagine a universe so young that no planets, no galaxies, not even a single speck of dust existed, just an endless sea of hydrogen and helium swirling in the darkness. This was the stage for the very first stars, known to astronomers as population 3 stars. Unlike the stars we see today, these ancient giants were made of nothing but the raw ingredients of the Big Bang. No carbon, no oxygen, no iron, just the simplest elements in existence. And because of that purity, they burned differently, wildly, violently, with a ferocity we can barely comprehend. Scientists believe these stars could have been hundreds, maybe even thousands of times more massive than our Sun. Picture a star so colossal it could dwarf entire solar systems, shining with a brilliance that outshone entire galaxies. But that brilliance came at a cost. Fueled only by hydrogen and helium, these stars lived fast and died young, some lasting only a few million years before exploding in cataclysmic supernova. And it's those explosions that changed everything. The intense heat and pressure in their cores forged heavier elements for the first time. Carbon, nitrogen, oxygen, the very building blocks of life as we know it. But here's the twist, we've never actually seen a population 3 star. They vanished billions of years ago, leaving behind only faint chemical fingerprints in the oldest corners of the universe. Some researchers think their remnants might still be hiding in the form of supermassive black holes, lurking at the centers of galaxies. Others speculate that traces of their existence are embedded in the light from the most distant quasars, waiting to be decoded. One thing's certain, without these primordial giants, the universe as we know it, the planets, the stars, even us, wouldn't exist. They were the cosmic alchemists, turning simplicity into complexity, darkness into light. And their legacy is written in every atom of our bodies, every spark of life in the cosmos. Detecting these elusive first stars isn't just difficult, it's like trying to spot a single candle flame from across the universe. The reason population 3 stars existed during what scientists call the cosmic dark ages, a time so early that light itself was still battling to pierce through the fog of the newborn universe. By the time their glow could have reached us, space had expanded so much that their light stretched into near invisibility, a phenomenon known as redshift. Think of it like an ambulance siren fading as it drives away. Except here, the siren is a star, and it's been driving away for over 13 billion years. Our current telescopes, even the most advanced like the James Webb Space Telescope, are straining to catch whispers of these ancient giants. The issue isn't just distance, it's the sheer rarity of these stars. They likely formed in isolation, scattered across vast, empty stretches of the early cosmos, making them incredibly hard to pinpoint. Plus, their short lifespans mean they burned out long before most galaxies even began taking shape. Researchers often compare it to searching for fossils of the very first life on Earth, except these fossils are made of light, and they're drifting in an ocean of expanding space. But there's another twist. When these stars died, they didn't just vanish. Their explosions seeded the universe with heavier elements, leaving behind chemical signatures that linger in the atmospheres of younger stars. Astronomers hunt for these traces like detectives sifting through cosmic fingerprints, looking for stars with almost no metals, a telltale sign they formed from the remnants of population 3. Some teams are even listening for echoes of their deaths in gravitational waves, the ripples in space-time from their cataclysmic collapses. The challenge isn't just technical, it's a race against time itself. The farther back we look, the fainter the signals become, buried under eons of cosmic noise. Yet every faint clue we uncover brings us closer to solving one of astronomy's greatest mysteries: how the universe's first lights flickered on, and how they set the stage for everything that followed. Dark matter, that mysterious, invisible substance making up most of the universe's mass, might have been the unseen architect behind the birth of the first stars. While we can't see it or touch it, its gravitational pull could have sculpted the early cosmos, creating dense pockets where ordinary matter pooled like water in a bowl. Picture this: in the darkness of the infant universe, dark matter began clumping together, forming vast, invisible scaffolding. These clumps acted like cosmic traps, their gravity pulling in clouds of hydrogen and helium until the gas grew so dense and hot that nuclear fusion ignited, and the first stars flared to life. But here's where it gets controversial. Some models suggest dark matter was the only force strong enough to gather gas efficiently in those early days, while others argue that turbulence and shocks from the Big Bang played an equally crucial role. There's even a wild theory that dark matter itself might have been slightly warm, moving fast enough to smooth out smaller clumps, leaving only the largest structures to form stars. If true, that would mean the very first stars were exceptionally rare and monstrously big, scattered far apart in a universe still finding its feet. The problem: we still don't fully understand how dark matter behaves on these tiny, ancient scales. Modern simulations struggle to recreate conditions so extreme, leaving gaps in the story. For instance, did dark matter's pull create stars in isolation, or did it trigger cascades of star formation, lighting up entire regions at once? And what about the leftovers? Could those primordial dark matter halos still linger today, hiding in plain sight? Whatever the answers, one thing's clear: without dark matter's invisible hand, the universe might have remained a cold, starless void forever. This isn't just about the past, though. Unraveling dark matter's role could help explain why some galaxies today are brimming with stars while others are eerily empty. It's like piecing together a cosmic recipe where the first ingredients, dark matter and gas, determined the flavor of everything that followed. And until we can peer even deeper into the universe's infancy, the mystery of how exactly these forces conspired to spark the first starlight remains one of astronomy's greatest puzzles. The death of a population 3 star wasn't just an explosion, it was a cosmic reset button. When these behemoths ran out of fuel, some didn't just fade away. They collapsed inward with such force that not even light could escape, birthing the universe's very first black holes. But these weren't the ordinary black holes we detect today. They were primordial monsters, packing the mass of thousands of suns into a space smaller than our solar system. And according to one groundbreaking theory, These ancient black holes might have been the seeds that grew into the supermassive beasts lurking at the hearts of galaxies today. Take quasars, for example. These blazing objects, some shining brighter than 1,000 galaxies, are powered by supermassive black holes feeding on surrounding matter. But here's the puzzle. Quasars existed when the universe was less than 1 billion years old, far too young for black holes to have grown so huge through normal means. Unless, of course, they started with a head start, enter the first stars. If just a handful of them collapsed directly into black holes, those seeds could have devoured surrounding gas at breakneck speed, ballooning into the supermassive giants we see lighting up quasars. It's like planting a redwood seed and waking up to a fully grown tree overnight. Nature doesn't work that way unless something extraordinary happened first. There's another clue hidden in the way galaxies form. Supermassive black holes and their host galaxies seem to grow in lockstep, as if their fates were intertwined from the beginning. But why? One explanation is that the first black holes didn't just sit there, they shaped their surroundings. As they fed, their immense gravity funneled gas into dense streams, sparking waves of star formation and sculpting the earliest galactic structures. In this view, the universe's first stars didn't just light up the cosmos, their deaths built the scaffolding for everything that came after. Not everyone agrees, of course. Some researchers argue that supermassive black holes could have formed through other means, like the direct collapse of giant gas clouds. Others point out that even the heaviest population, 3 stars, might not have left behind black holes large enough to explain quasars. But here's what's tantalizing. If we could find just one relic of those first-generation black holes, perhaps a quiet, middleweight black hole drifting in deep space, it could be the smoking gun that cracks this cosmic case wide open. Until then, the mystery of how darkness gave birth to light, and how light then forged the engines of the universe, remains one of the most thrilling unsolved stories in astrophysics. We've been picturing the first stars as solitary giants, blazing alone in the void, but what if they weren't loners at all? Cutting-edge simulations now suggest that many of these primordial stars might have formed in pairs or even tight-knit clusters, dancing around each other in gravitational embraces. This changes everything. Binary or multiple star systems don't just look different, they behave differently. Their lives are shaped by stellar tug-of-wars, mass transfers, and explosive interactions that single stars never experience. And in the early universe, where conditions were unimaginably dense and chaotic, these cosmic partnerships could have been far more common than we ever suspected. Take a pair of young, massive stars orbiting each other. As they age, the larger star burns through its fuel faster, eventually swelling into a monster that spills its outer layers onto its companion. This stolen gas can rejuvenate the smaller star, extending its life while dooming the donor to an early collapse. But here's where things get wild. When the more massive star finally explodes as a supernova, the blast can kick its surviving partner like a cosmic slingshot, hurling it across space at incredible speeds. Some astronomers believe this might explain mysterious runaway stars we've spotted in distant galaxies, ancient survivors of these violent breakups. Then there's the supernova themselves. In a binary system, the explosion of one star doesn't just light up the cosmos. It bathes its companion in a flood of radiation and shock waves, altering its chemistry and future evolution. Some models suggest these interactions could have produced supernova with unusual energy signatures, explaining puzzling gaps in our observations of the early universe's chemical makeup. Even more intriguing, if both stars in a binary were massive enough, their deaths could leave behind paired black holes or neutron stars, setting the stage for eventual collisions that would shake spacetime with gravitational waves. But why does this matter beyond stellar drama? Because these systems were cosmic factories. Binary stars can forge heavier elements more efficiently than solo stars, thanks to their turbulent interactions. The gold in your jewelry, the uranium in nuclear reactors. These elements might owe their existence to the chaotic dances of the first star pairs, and if clusters of stars formed together, their combined radiation could have ripped apart nearby gas clouds, delaying the birth of future stars and shaping entire galaxies before they even fully formed. The evidence is still circumstantial, scattered like breadcrumbs across the cosmos. Faint chemical imbalances in ancient stars, odd patterns in gravitational wave signals, even the peculiar motions of some of the universe's oldest objects, all hint that stellar teamwork was part of the universe's blueprint from the very beginning. It's a humbling thought. The night sky's serene twinkle might have roots in the frantic, entangled lives of stars that died before Earth even existed. And if we're right about this, it means the first chapter of cosmic history wasn't just a story of solo acts, it was an epic ensemble performance written in fire and gravity. For decades, astronomers assumed the first stars had to be enormous colossal furnaces hundreds of times heavier than our Sun, but nature loves breaking rules. New simulations reveal a twist. The chaotic, turbulent gas clouds of the early universe might have shredded these would-be giants into smaller pieces before they could fully form. Think of it like trying to roll a single massive snowball in a hurricane. The violent winds keep tearing chunks away, leaving behind a scattered pile of smaller snowballs instead. This turbulence wasn't just random noise. In the aftermath of the Big Bang, space crackled with energy shockwaves from collapsing dark matter, bubbles of heated gas, and collisions between streaming flows of primordial hydrogen. These chaotic motions stirred the cosmic pot, preventing gas from pooling smoothly into single, monolithic stars. Instead, dense knots fractured apart, each fragment collapsing into its own stellar core. Some models suggest this could have spawned stars as small as 10 solar masses, still titanic by today's standards, but a far cry from the thousand-sun behemoths we once imagined. Here's where it gets messy. Turbulence doesn't just split gas clouds, it changes how they cool. Normally, hydrogen atoms shed heat by radiating energy, allowing gas to condense into stars. But turbulence can trap heat, creating pockets too warm to collapse easily. The result, a stuttering stop-start process where some regions form stars rapidly while others stagnate. This might explain why the first starlight didn't flood the universe all at once, but flickered on gradually, as if the cosmos itself was nervously testing the waters. The implications are huge. If population 3 stars came in varied sizes, their deaths would have sprayed space with a wider mix of elements. Smaller stars live longer, cooking their fuel more slowly and shedding enriched material less violently than their supermassive cousins. That could solve a long-standing puzzle: why some ancient gas clouds we've observed carry traces of lighter elements but lack the heavier metals we'd expect from monster stars. Turbulent fragmentation might have been the universe's way of diversifying its stellar portfolio from the very beginning, yet the debate isn't settled. Critics point out that turbulence requires precise conditions too little, and gas collapses into giants too much, and stars might not form at all. It's a cosmic balancing act, and we're still piecing together how the early universe walked that tightrope. One clue might lie in black hole mergers detected by gravitational wave observatories. Some of these collisions could involve remnants of fragmented first stars, their masses telling a story of the chaos that birthed them. Until then, the idea that turbulence shaped the first starlight remains a tantalizing possibility, reminding us that even in its infancy, the universe was anything but predictable. Pinpointing the exact moment the universe's first stars flickered to life is like trying to catch the very first raindrop in a storm. Estimates vary wildly. Some researchers argue starlight pierced the cosmic darkness just 100 million years after the Big Bang, while others insist it took nearly 1 billion years. This isn't just academic quibbling. That gap represents a chasm in our understanding of how quickly the infant universe transitioned from a featureless void to a structured cosmos brimming with light. The debate hinges on two competing forces: gravity's relentless pull and the universe's stubborn resistance to change. Picture a tug of war between dark matter's invisible scaffolding slowly gathering hydrogen into dense clumps, and the searing heat left over from the Big Bang, which kept gas too energetic to collapse smoothly. Some simulations suggest pockets of gas could have cooled rapidly in particularly dense regions, sparking early starbursts. Others model a more sluggish timeline, where the universe needed eons to shed enough heat for gravity to finally win. Enter the James Webb Space Telescope, our most powerful time machine. Peering deeper into the infrared than any instrument before it, Webb has already spotted galaxies shining when the universe was less than 300 million years old, astonishingly early by previous standards. But here's the puzzle. These galaxies look suspiciously mature, as if star formation had been underway long before we're seeing them. It's like discovering a bustling city in ruins and realizing its foundations must be far older than anyone guessed. One explanation: the very first stars might have been lonelier pioneers than we thought. Instead of lighting up the cosmos in a coordinated dawn, they could have flickered on sporadically, isolated beacons in the darkness that preheated surrounding gas, delaying widespread star formation until later epochs. This would create a patchy timeline where some regions of space saw starlight shockingly early while others lingered in darkness. New clues are emerging from an unexpected source: the cosmic microwave background. Subtle distortions in this afterglow of the Big Bang hint at when ultraviolet light from early stars began stripping electrons from hydrogen atoms, a process called reionization. Current data suggests this didn't happen all at once but in waves, supporting the idea of a drawn-out, uneven cosmic dawn. The stakes couldn't be higher. If stars ignited earlier than expected, it challenges our models of dark matter's role in structuring the universe. If later, it means something suppressed star formation, perhaps turbulence, magnetic fields, or even exotic physics we haven't yet imagined. Every new sliver of light Webb captures from the edge of time isn't just rewriting history. It's revealing how resilient and creative the universe was in its youth, finding countless ways to kindle its first fires against all odds. Dark matter wasn't just a passive bystander in the birth of the first stars, it may have been their cosmic cradle. Picture an invisible web of dark matter halos, each one a dense knot of mysterious particles woven into the fabric of the early universe. These halos acted like gravitational anchors, drawing in swirling clouds of hydrogen gas until the pressure became unbearable. Then ignition. The first stars flared to life, not in isolation but cocooned within these vast, unseen structures. But here's what makes them truly strange. Their light might have carried a fingerprint of dark matter's influence, a spectral signature we could still decode today. Unlike modern stars, which often form in bustling galactic neighborhoods, these early stars burned in near-total darkness. Their dark matter halos shielded them from disruptive forces, allowing gas to collapse into stars with terrifying efficiency. Some models suggest this process could have birthed stars up to 1,000 times more massive than our Sun stellar titans, fueled by pure hydrogen, their cores running hotter and brighter than anything we see now. But the real giveaway, their radiation. Dark matter's gravity would have compressed these stars so tightly that their ultraviolet light carried a distinct high-energy spike, like a scream echoing through the cosmos. If we could spot that telltale glow in the farthest reaches of space, it'd be smoking gun evidence of dark matter's role in lighting up the universe. There's a twist, though. Some theorists argue these halos didn't just nurture stars, they might have strangled them. As dark matter particles collided in the halo's core, they could have released bursts of energy, heating the surrounding gas and preventing it from cooling into new stars. It's a cosmic paradox. The same force that birthed the first generation of stars might have also ensured their extinction. That could explain why population 3 stars vanished so quickly, leaving behind only chemical ghosts in the atmospheres of younger stars. Hunting for these signatures isn't just about rewriting history, it's about solving a modern mystery. Astronomers are scouring quasar light for unusual absorption lines, hunting for traces of gas that was ionized by those primordial stars. Others are refining telescopes to catch the faint infrared whispers of their remnants, redshifted beyond recognition. It's like tuning a radio to a station that stopped broadcasting billions of years ago, hoping to catch one last note of a song that shaped everything. The implications stretch far beyond stellar origins. If dark matter halos really did mold the first stars, it means the invisible scaffolding of the universe didn't just structure galaxies. It dictated how light itself first pierced the darkness. And if we ever manage to detect that elusive radiation signature, it won't just confirm a theory. It'll reveal the moment dark matter and starlight shook hands, setting the cosmos on the path to everything we know. Zero metal stars sounds impossible, right? After all, even the cleanest lab on Earth can't eliminate every trace of contamination. But in the pristine early universe, the first stars might have come close. These hypothetical giants, known as zero metallicity stars, would have formed from gas untouched by any element heavier than helium. No carbon, no oxygen, nothing but hydrogen and the barest whisper of helium forged in the Big Bang's aftermath. The difference between these and later stars isn't just academic. Without metals to help cool collapsing gas clouds, the physics of star formation flips on its head, leading to structures so bizarre they defy what we see today. Here's why metals matter in modern star birth. When a gas cloud collapses, atoms like carbon and oxygen emit radiation as they collide, shedding heat and allowing the cloud to shrink further. But in a zero-metal environment, hydrogen can only cool so efficiently, relying on rare molecular hydrogen interactions that are thousands of times weaker. The result, gas struggles to shed heat, resisting fragmentation. Simulations suggest this could have produced stars with almost no upper limit to their size, colossal behemoths reaching 500 solar masses or more, their cores burning at temperatures that would make modern stars look like campfires. But there's a catch. Even the early universe might not have been perfectly pure. Cosmic inflation could have scattered microscopic traces of lithium or beryllium, forged in the Big Bang's first minutes, while quantum fluctuations may have created localized pockets where rare, heavier elements briefly clustered. These contaminants, though absurdly scarce by today's standards, might have been enough to trigger subtle changes. A single lithium atom per trillion hydrogen atoms could have altered cooling rates just enough to fracture a collapsing cloud into multiple smaller stars instead of one unstoppable monster. The hunt for proof is on. Astronomers scour the spectra of ultra-distant quasars, searching for absorption lines that might betray the presence of these mythical zero-metal stars. Others simulate their hypothetical supernova, predicting unique elemental signatures like a surge of helium and a puzzling absence of iron that could linger in second-generation stars. The most tantalizing clue, a handful of ancient stars in our own galaxy, like the famous SMSS J03 1300, contain almost no detectable metals. They're not perfect zeros, but they might be the closest survivors of that primordial era, carrying echoes of a time when the universe hadn't yet learned how to make stars the way it does now. What's at stake isn't just a footnote in stellar evolution. If zero-metal stars existed, their supernova would have unleashed energy unlike anything since, flooding the cosmos with a distinct mix of elements that seeded future generations. Their black hole remnants could be the missing link in explaining supermassive black holes' rapid growth, and their very existence would prove that the universe's first starlight wasn't just a dimmer version of what we see today. It was a fundamentally different kind of fire, burning under rules we're only beginning to decode. Until we find definitive evidence, these stars remain both a cornerstone of cosmic theory and one of its most elusive ghosts. When a population 3 star reached the end of its brief, fiery life, it didn't just vanish, it shattered the universe's status quo. These cosmic explosions, far more violent than anything seen today, blasted newly forged elements into the void like celestial farmers scattering seeds. Carbon, oxygen, silicon, even traces of iron elements that hadn't existed before were suddenly hurled across light years, enriching the primordial gas clouds with the raw materials for everything to come. This wasn't just destruction, it was the universe's first act of creation beyond hydrogen and helium, a process so vital that without it, planets, oceans, and life itself could never have formed. The sheer scale of these supernovae defies imagination. Picture a star hundreds of times more massive than our Sun, detonating with the energy of 1 billion atomic bombs. The shockwaves alone could rip through neighboring gas clouds, compressing them so violently they collapsed into new stars almost instantly. But the real magic happened in the explosion's heart. For the first time, atomic nuclei fused under pressures so extreme they formed elements heavier than helium, a process called nucleosynthesis. These weren't just trace amounts. A single supernova could vomit out enough oxygen to seed thousands of future solar systems, all while spewing radioactive isotopes like aluminum-26, which acted as cosmic clocks as they decayed. Here's what's wild: these explosions didn't just spread elements evenly. Some regions got dusted lightly, like sprinkles on a cupcake, while others were drenched in heavy elements, creating bizarre chemical hotspots. Astronomers call this patchy enrichment, and it explains why some ancient star clusters show puzzling variations in their metal content. Imagine two siblings born from the same parent star's debris, but one grew up surrounded by gold and platinum while the other got mostly nitrogen and carbon, a cosmic lottery with consequences that echoed for billions of years. The legacy of these explosions isn't just locked in the past. We're still finding their fingerprints today. Ultra-old stars in our galaxy's halo, like He 1523-0901, contain barely any iron but show surprising bursts of carbon and oxygen, a chemical signature that matches exactly what theorists predict from first-generation supernova. Even more telling, the gas between galaxies isn't perfectly pristine. Deep spectroscopic scans reveal it's laced with elements that could only have come from those primordial blasts, meaning we're literally swimming in the ashes of the universe's first fires. But here's the twist: some of these supernovae might have been too powerful for their own good. Models suggest the most massive stars could have collapsed into hypernova, explosions so energetic they sterilized entire regions of space, blasting gas clear out of their host dark matter halos. This could explain why certain patches of the early universe stayed bizarrely empty for eons, like cosmic dead zones where star formation was snuffed out before it could really begin. Yet even these destructive monsters played a role. By carving voids, they created pressure waves that triggered star birth elsewhere, proving that in the cosmos, death and creation are two sides of the same coin. What's astonishing isn't just that these explosions happened, it's how perfectly they set the stage for complexity. The exact mix of elements they produced, from life-giving carbon to planet-forming silicon, feels almost tailor-made for what came next. Too little enrichment, and later stars would have lacked the materials to build rocky worlds. Too much, and the universe might have choked on heavy elements before life could emerge. It's as if those first supernovae weren't just random acts of violence, but the universe's first deliberate step toward building a home for itself and for us. Some of the first stars might not have just burned alone, they could have ignited cosmic chain reactions, setting off runaway waves of star formation that lit up the early universe like fireworks. Picture a single massive star, blazing with such intensity that its ultraviolet radiation didn't just illuminate the darkness, it tore electrons from hydrogen atoms in a process called ionization. This transformed cold, dense gas clouds into hot, charged plasma, preventing them from collapsing into new stars, at least temporarily. But here's the twist: when those ionized regions finally cooled, they didn't just return to their original state. Instead, shock waves from the cooling gas created dense, rippling shells at their edges, like frost forming on a window, and in those shells gravity found its opportunity. Compressed and destabilized, the gas fractured into clumps, each one a potential seed for a new star. The original star didn't just die, it essentially built a nursery for its successors. Some simulations suggest this domino effect could have spawned entire clusters of secondary stars within just a few million years, far faster than star formation typically occurs today. It's as if the first stars were cosmic arsonists, setting fires so intense they sparked blazes light years away. But there's another layer to this phenomenon. The radiation from these secondary stars would have then ionized their surroundings, continuing the cycle. Over time, this could have created expanding bubbles of star formation, like concentric rings spreading out from a pebble dropped in water. Astronomers call this positive feedback, and it might explain why the early universe transitioned from total darkness to a glittering cosmic landscape so quickly. Some regions could have experienced multiple generations of stars in the time it takes modern galaxies to form even one. The evidence for this theory lies in the peculiar distribution of ancient star clusters. Certain patches of the universe show stars of nearly identical ages packed closely together, as if they all formed in rapid succession. Others reveal chemical similarities between stars light years apart, hinting they were birthed from the same enriched debris. Even the arrangement of some of the oldest globular clusters, those dense, ancient swarms of stars orbiting galaxies like our Milky Way, could be frozen relics of these runaway chains, their tightly packed orbits preserving the memory of their frantic origins. Yet not all theorists are convinced. Critics argue that the early universe's harsh environment, riddled with turbulence and competing radiation, might have disrupted these delicate feedback loops before they could gain momentum. And if the first stars were as massive as suspected, their supernova could have blown away nearby gas entirely, starving potential successors before they had a chance to form. It's a cosmic balancing act. Too much radiation and star formation shuts down, too little and nothing triggers the next wave. That's why researchers are scouring the most distant galaxies for clues. If runaway star formation really happened, we might spot telltale patterns like stars arranged in concentric shells or bizarre age gaps between stellar populations. Others are simulating these processes on supercomputers, tweaking variables like radiation intensity and gas density to see if they can recreate the universe's first great chain reaction. The answer could redefine how we see the cosmos's earliest chapters, not as a slow awakening, but as a frenzied sprint toward light, with each newborn star passing the torch to the next. Magnetic fields are often overlooked silent players in the cosmic drama of star formation, but what if they were the invisible conductors orchestrating the universe's first stars? The idea that primordial magnetic fields could have shaped these ancient giants is one of astrophysics' most hotly debated theories. Unlike today's stars, which form in environments laced with magnetic fields from previous stellar generations, the first stars emerged in a universe where magnetism might have been woven into the fabric of space itself. The question isn't just whether these fields existed, it's whether they were strong enough to twist collapsing gas clouds into entirely new shapes, altering the very blueprint of stellar birth. Simulations paint a tantalizing picture. In a universe without magnetic fields, gas collapses inward symmetrically, like water swirling down a drain. But add even a whisper of magnetism and everything changes. Magnetic fields create tension, acting like cosmic rubber bands that resist twisting and compression. This could have prevented gas clouds from fragmenting into multiple small stars, instead funneling material into single, monstrously massive stars. Some models suggest fields as weak as a trillionth of Earth's magnetic strength, far too faint to detect directly, might have been enough to tip the scales, explaining why population 3 stars were so unlike anything we see today. The controversy deepens when you consider polarization. Light from the cosmic microwave background, the universe's oldest radiation, shows faint patterns of polarization that some researchers believe could be fingerprints of these primordial fields. If true, it would mean magnetism wasn't just present, it was powerful enough to leave scars on the cosmos itself. Other clues come from distant quasars whose light passes through ancient gas clouds that might still bear the imprint of early magnetic turbulence. It's like finding fossilized ripples in a pond that dried up billions of years ago. Yet skeptics argue these signals could have simpler explanations. Perhaps the polarization patterns come from later magnetic fields, stirred up by galaxy formation rather than dating back to the Big Bang. Others point out that the first star's extreme heat would have ionized surrounding gas, potentially erasing any primordial magnetic traces before they could be preserved. The debate hinges on a cosmic chicken and egg problem. Did magnetism shape the first stars, or did the first stars create the conditions for magnetism to thrive? What's at stake isn't just a footnote in astrophysics. If primordial fields were key players, they could explain puzzling gaps in our understanding, like why some regions of the early universe formed stars shockingly fast while others lagged behind. Magnetic fields might have acted as cosmic traffic controllers, directing gas flows and determining where and how the universe's first lights flickered on. Until we decode those faint polarization signals or simulate the early cosmos with even greater precision, the role of magnetism remains one of the most electrifying unsolved mysteries of the cosmic dawn. What if stars didn't need nuclear fusion to shine? Imagine a celestial object so bizarre, it draws energy from the annihilation of dark matter itself. These hypothetical monsters, dubbed dark stars, could rewrite everything we know about stellar evolution. Unlike ordinary stars that burn hydrogen in their cores, dark stars would feed on the gravitational collapse of dark matter particles surrounding them, producing heat and light through an entirely different process. And the craziest part, they might still be out there, lurking in the distant cosmos, defying the laws of conventional astronomy. The theory hinges on dark matter's peculiar properties. While invisible and intangible to normal matter, dark matter particles could theoretically collide and annihilate each other, releasing bursts of energy. In the early universe, where dark matter was densely packed, these collisions would have been frequent enough to power an entire star. Picture a vast sphere of hydrogen and helium, its core packed with swirling dark matter. As particles annihilated, they'd flood the star with heat, preventing it from ever needing to ignite nuclear fusion. The result, a star that glows not from fire, but from the eerie, invisible decay of the universe's most mysterious substance. Dark stars wouldn't just look different, they'd behave differently. Without the fierce internal pressures of fusion, they could grow to staggering sizes, some models suggesting up to 10 million times the mass of our Sun. Their surfaces would be cooler than normal stars of similar size, emitting a dim, reddish glow. Most unsettling of all, they might never die. While conventional stars exhaust their fuel in millions or billions of years, a dark star could theoretically last trillions, persisting long after normal stars have flickered out, sustained by the slow but steady annihilation of dark matter. The hunt for these phantoms is already underway. Astronomers scour ancient galaxies for objects that match the predicted infrared signatures of dark stars, while others analyze anomalies in the cosmic microwave background for hints of their early influence. One tantalizing candidate, a bizarre object dubbed J2014+057, emits light patterns that defy traditional stellar models, though skeptics argue it could just be an unusual quasar. What keeps this theory alive isn't just the allure of discovery, it's the staggering implications. If dark stars existed, their slow decay could have seeded the universe with unique particles, altering the chemical makeup of early galaxies. Their remnants might even explain some of the missing dark matter we can't account for today. And if by some miracle one still burns in some distant corner of space, finding it wouldn't just confirm a wild theory, it'd force us to redefine what a star even is. Until then, dark stars remain one of astrophysics' most electrifying what-ifs, a reminder that the cosmos still holds secrets wilder than fiction. The James Webb Space Telescope might be humanity's best shot at catching a glimpse of these elusive dark stars if they exist. Unlike traditional telescopes that focus on visible light, Webb's infrared eyes are perfectly tuned to spot the cold, reddish glow these objects would emit. But finding one isn't as simple as pointing the telescope at the sky and waiting for a dark star to wave back. Astronomers are hunting for specific, bizarre signatures, objects that shine too dimly for their colossal size or whose light spectra lack the telltale chemical fingerprints of fusion-powered stars. It's like searching for a shadow in a room lit only by candlelight, except the shadow might be 1,000,000 times larger than the sun. One key clue lies in the ratio of helium to hydrogen. In normal stars, fusion constantly alters this balance, but dark stars powered by particle annihilation would preserve a more primordial mix, untouched by stellar nucleosynthesis. Another giveaway could be their temperature. While a fusion star of similar mass would blaze at tens of thousands of degrees, a dark star might hover at just a few thousand, radiating mostly in the infrared. If Webb spots an object in the early universe that's massive yet suspiciously cool, with light patterns that defy conventional models, it could be staring at something far stranger than a galaxy or quasar. The implications of such a discovery would send shockwaves through astrophysics. For starters, it would confirm that dark matter isn't just an invisible gravitational glue holding galaxies together. It's interactive enough to power entire stars. That alone would narrow down the list of possible dark matter particles, ruling out theories where they're completely inert. Even wilder, dark stars could solve the puzzle of how supermassive black holes grew so quickly in the young universe. If these stars collapsed directly into black holes without the usual supernova fireworks, their remnants might have served as ready-made seeds, skipping millions of years of gradual growth. But the hunt isn't without controversy. Some researchers argue that what looks like a dark star could just be an unusually dusty galaxy or a rare type of active black hole. Others point out that even Webb has limits. Its vision might not be sharp enough to distinguish a single dark star from a cluster of smaller objects. And then there's the timing problem. If dark stars were common, why haven't we seen any indirect traces of them in the cosmic microwave background or the distribution of ancient gas clouds? Despite the challenges, the search is gaining momentum. Teams are combing through Webb's deepest infrared surveys, training machine learning algorithms to flag anomalies that human eyes might miss. One promising candidate already made headlines: a faint, massive object dubbed J2242+0359 that emits light matching dark star predictions, though skeptics argue it's more likely a peculiar quasar. The debate rages on, but one thing's certain: if definitive proof emerges, textbooks will need rewriting. Dark stars wouldn't just be a new class of object, they'd be a window into physics operating under rules we've barely begun to imagine. And that's the real stakes of this hunt. Beyond reshaping our understanding of stellar evolution, discovering dark stars would force us to confront a universe where ordinary matter isn't the sole architect of cosmic structures. It's humbling to think that the night sky, already full of wonders, might be hiding entire categories of celestial objects powered by forces we can't see or touch. Every strange blip in Webb's data could be the first hint of a cosmos even more mysterious than we dared dream. Quasi-stars sound like something ripped straight from a sci-fi novel, cosmic hybrids so bizarre they blur the line between star and black hole. Imagine a star so massive, its core collapses into a black hole while its outer layers stubbornly cling on, creating a celestial paradox, a black hole wrapped in a shroud of burning plasma. These theoretical monsters, known as quasi-stars, could have been the universe's ultimate powerhouses, bridging the gap between the first stars and the supermassive black holes that dominate galaxies today. Here's how they might have worked. A typical population 3-star, hundreds of times more massive than our Sun, would normally explode or collapse in a violent supernova. But in the dense, gas-rich environment of the early universe, something stranger could have happened. As the star's core imploded into a black hole, the surrounding layers, still packed with fresh hydrogen, might have resisted total collapse. Instead of being devoured, this gas would have spiraled inward in a vast accretion disk, releasing enough heat and radiation to keep the outer layers shining for thousands of years. The result, a star with a black hole heart powered not by fusion, but by the slow, gluttonous feast of its own core. The scale is almost incomprehensible. A single quasi-star could span the width of our solar system, its outer edges glowing with the warmth of a normal star while its core lurked as a singularity. Unlike modern stars, which fuse hydrogen into helium at a steady pace, a quasi-star's energy output would have been erratic, flaring as the black hole gulped down gas in fits and starts. Some models suggest their luminosity could have rivaled small galaxies, casting shadows across cosmic distances. But why would these freaks of nature matter? Because they might solve one of astrophysics' biggest headaches: how supermassive black holes grew so big, so fast. A typical black hole forms from a dying star and takes eons to grow by sucking in gas. But a quasi-star's black hole core would have started with a massive head start, hundreds or thousands of solar masses, and had a built-in buffet of surrounding material to devour. In just a few million years, it could have ballooned into the kind of supermassive beast we see powering quasars in the early universe. It's like finding a toddler who's already 6 feet tall. You'd wonder what on earth they'd been eating. There's another tantalizing possibility. Quasi-stars might have been cosmic chemists. While normal stars forge elements through fusion, the intense radiation and turbulence around a quasi-star's accretion disk could have cooked up exotic isotopes, spitting them into space when the outer layers finally dissipated. Some researchers speculate this process might explain mysterious pockets of unusual elements in ancient star clusters, chemical anomalies that don't fit standard supernova models. Of course, proving they existed is another challenge. Quasi-stars would have been short-lived by cosmic standards, vanishing once their outer gas was exhausted. Any remnants would now be supermassive black holes, indistinguishable from those formed by other means. The best hope for evidence lies in their hypothetical byproducts, perhaps a peculiar distribution of elements in the universe's oldest stars, or even gravitational wave signatures from their eventual collapse. Until then, quasi-stars remain one of astrophysics' most captivating what-ifs, a reminder that the early universe was a laboratory for extremes we're only beginning to imagine. What's striking isn't just their strangeness, it's their elegance as a missing link. In a cosmos that loves transitions, quasi-stars would have been the ultimate intermediaries, turning the death throes of the first stars into the birth cries of the first black holes. They embody a universe experimenting, finding new ways to bend its own rules. And if they did exist, they'd prove that sometimes the most powerful forces in creation emerge from the most unstable balancing acts, a star clinging to life even as its heart turns to darkness. Picture the early universe not as a blank void, but as a sprawling web of filaments, threads of dark matter, and gas stretching across billions of light years like cosmic highways. These weren't just passive structures, they were stellar assembly lines, funneling pristine hydrogen and helium into dense knots where gravity could work its magic. Recent simulations reveal something astonishing. The first stars might not have formed in isolated pockets, but along these glowing filaments, igniting like a string of streetlights flickering on in the pre-dawn darkness. The key lies in how gas behaved in this primordial labyrinth. Without galaxies or planets to disrupt the flow, hydrogen and helium streamed along these filaments like water racing through riverbeds, colliding at intersections where the density became unbearable. At certain nodes, the pressure grew so intense that gas clouds collapsed directly into stars, not one at a time but in cascading waves. Think of it like traffic piling up at a freeway interchange, except instead of cars, it's raw star fuel, and the accidents create stars instead of gridlock. What's mind-bending is the scale. Some of these filaments could have stretched for thousands of light years, with stars forming in beads along their lengths like dew on a spider's web. Unlike modern star-forming regions, which are messy and clustered, these stellar chains would have appeared eerily precise, their spacing dictated by the rhythm of gas flow and shock waves rippling through the early cosmos. Simulations suggest this process could have produced stars of wildly different sizes, some modest by primordial standards at 50 solar masses, others ballooning to 500 or more, all strung along the same luminous thread. The implications rewrite how we imagine cosmic dawn. If stars ignited along filaments, their radiation wouldn't have been scattered randomly. It would have flooded the surrounding channels, ionizing gas in focused jets and potentially accelerating star formation in neighboring nodes. This could explain why some regions of the early universe seem to have lit up almost synchronously, as if a switch had been flipped. Even more intriguing, the remnants of these filaments might still be detectable today. Astronomers using telescopes like the European Space Agency's Euclid mission are mapping the cosmic web's faint glow, hunting for subtle overdensities of stars or gas that could trace back to these ancient stellar assembly lines. Yet mysteries remain. Why didn't every filament node ignite a star? Some theories suggest turbulence, random eddies in the gas flow might have disrupted collapse in certain areas, leaving stretches of the cosmic highway dark. Others point to magnetic fields, which could have braided the filaments like ropes, pinching some regions tight while leaving others loose. There's even a wild possibility that the first black holes, born from early star deaths, could have redirected gas flows midstream, shutting off star formation in some filaments entirely. The beauty of this theory isn't just its elegance, it's how it connects the universe's largest structures to its smallest lights. Those filaments weren't just scaffolding, they were the universe's first power grids, transmitting not electricity but the raw materials for creation itself. And if we're right, every star we see today, even our own sun, might owe its existence to the ghostly highways that once lit up the cosmos, one brilliant bead at a time. Among the universe's most elusive particles, sterile neutrinos might have played a hidden role in shaping the first stars. Unlike their ordinary neutrino cousins, which interact via the weak nuclear force, sterile neutrinos barely interact with anything at all, passing through matter like ghosts through walls. Yet in the extreme conditions of the early cosmos, their presence could have subtly altered the fate of collapsing gas clouds, slowing or speeding up star formation in ways we're only beginning to understand. Here's the twist: sterile neutrinos don't just ignore matter, they might have influenced it indirectly by affecting how gas cooled. In a universe without metals, hydrogen relied on molecular hydrogen, two-bound atoms, to shed heat and collapse into stars. But sterile neutrinos, if they existed, could have emitted faint radiation as they decayed, gently warming the surrounding gas. Even a tiny temperature bump would have made it harder for hydrogen molecules to form, effectively putting the brakes on cooling. Picture a pot of water trying to boil with the lid slightly ajar. The heat escapes, but not fast enough. That delay might have stretched star formation timelines, allowing gas clouds to grow larger before fragmenting, potentially birthing more massive stars than we'd expect. The implications get stranger. Some models suggest sterile neutrinos could have clustered around dark matter halos, their combined gravity subtly warping gas flows. In regions dense with these particles, gas might have collapsed faster, creating pockets of accelerated star formation while leaving neighboring areas relatively barren. This could explain puzzling gaps in the distribution of ancient stars, like a cosmic patchwork where some threads burned bright while others remained stubbornly dark. Then there's the timing problem. If sterile neutrinos delayed cooling, the universe's first starlight might have flickered on later than current estimates predict. That aligns with recent James Webb observations of surprisingly mature galaxies in what should have been the cosmic dark ages. Could sterile neutrinos have pressed pause on star formation just long enough to let these galaxies build their foundations? Alternatively, their decay products might have left chemical fingerprints in primordial gas, traces we could hunt for in the spectra of the universe's oldest stars. Of course, not everyone's convinced. Detecting sterile neutrinos is notoriously difficult, and some physicists argue their effects would have been too minor to leave a mark. But if future telescopes uncover anomalies in early star clusters, unexpected temperature gradients, or oddly synchronized formation bursts, it might be the first hint that these phantom particles were pulling strings behind the scenes. What's certain is that the universe's first stars didn't form in a vacuum. Even the most elusive particles could have nudged their birth, proving that in cosmology, sometimes the quietest players leave the loudest echoes. Tiny black holes formed in the chaos of the Big Bang might have been the universe's first matchmakers, bringing gas together in cosmic introductions that led to stellar fireworks. These hypothetical objects, known as primordial black holes, could have been smaller than an atom yet heavier than a mountain, packing unimaginable density into vanishingly small spaces. And their gravitational pull, minuscule compared to modern black holes, might have been just enough to kickstart star formation when the universe was still taking its first breaths. Unlike black holes born from collapsing stars, primordial black holes could have formed in the first fraction of a second after the Big Bang, when extreme pressures squeezed matter into microscopic knots of spacetime. Some theories suggest they would have been everywhere, sprinkling the early cosmos like invisible seeds. As they drifted through clouds of hydrogen, their gravity, though faint, could have nudged nearby atoms into tighter clusters, creating dense pockets where gas collapsed faster than it otherwise would have. Picture a marble rolling through a cloud of dust, gathering specks in its wake. Now imagine that marble is 1 billion times heavier, and the dust is the raw material for stars. That's the kind of subtle but transformative influence these black holes might have had. The math gets even wilder. Because these black holes were so small, they'd emit Hawking radiation, a quantum quirk that makes them slowly evaporate over time. The smallest would have vanished almost instantly, but those with masses comparable to asteroids could have survived millions of years, long enough to witness the first stars flicker on. And as they decayed, their death throes might have injected bursts of energy into surrounding gas, heating it just enough to alter star formation in unpredictable ways. Some simulations suggest this could have produced stars with unusual compositions, their atmospheres laced with exotic particles forged in the black hole's final moments. There's a tantalizing piece of indirect evidence: the cosmic infrared background, a faint glow permeating the universe that can't be explained by known galaxies. Some researchers argue that evaporating primordial black holes could have contributed to this signal, their collective death flares leaving an imprint across the cosmos. Others point to mysterious gaps in the distribution of ancient star clusters, voids that might mark regions where primordial black holes were scarce, leaving gas too diffused to ignite stars efficiently. But the biggest question remains: if these black holes existed, where are they now? Most would have evaporated long ago, but a lucky few, those just massive enough to survive, might still lurk in the cosmos, drifting unseen through galaxies. Some astronomers are hunting for their telltale microlensing effects, brief flashes when a black hole passes in front of a distant star, warping its light like a cosmic magnifying glass. Others are searching for gravitational waves from collisions between these relics, which would ripple space-time with a distinctive high-pitched chirp. What's at stake isn't just another entry in the catalogue of cosmic oddities. If primordial black holes helped birth the first stars, they'd rewrite the story of cosmic dawn, proving that the universe's first lights weren't just born from chaos, they were midwifed by darkness. And if we ever catch one in the act, it would reveal a universe far stranger than we ever imagined, where the tiniest shadows played the biggest roles. When a first-generation star reached the end of its life, it didn't just explode, it rewrote the rules of destruction. The most massive among them likely died in spectacularly violent supernova, unlike anything witnessed today, with two particularly catastrophic variants dominating theories: pair instability supernova and hypernova. Both represent extremes of stellar death, but their mechanics and their lasting fingerprints on the cosmos couldn't be more different. Take pair instability supernova first. These occur in stars between 140 and 260 times the mass of our Sun, where the core becomes so hot that photons spontaneously transform into electron-positron pairs. Normally, photons provide outward pressure to support a star against collapse, but this conversion steals that pressure away. The core abruptly implodes, triggering runaway fusion that doesn't just explode the star, it completely obliterates it, leaving no black hole or neutron star behind. The energy released is staggering, up to 100 times brighter than a typical supernova, with enough force to blast away every last trace of the star's outer layers. The aftermath, a firework of newly forged elements from silicon to iron, sprayed into the void with unparalleled efficiency. These explosions were so thorough that they might explain why we've never found traces of certain supermassive star remnants. They were utterly erased from existence. Hypernova, on the other hand, were even more extreme and far messier. Theorized to occur in stars above 260 solar masses, these events produced collapsars, rapidly spinning cores that flattened into disks before collapsing into black holes. As material spiraled inward at near light speeds, twin jets of plasma shot outward along the rotation axis, piercing through the star like cosmic blowtorches. The result was an asymmetrical explosion, channeling energy in focused beams rather than a spherical blast. These jets, packed with gamma rays and heavy elements, could have traveled light years before dispersing, potentially explaining mysterious gamma ray bursts detected at the edge of the observable universe. What makes these deaths so consequential is how differently they enriched the cosmos. Pair instability supernova were democratic polluters, scattering elements evenly in all directions. Hypernova, by contrast, were precision artists, concentrating their chemical gifts along narrow corridors. This dichotomy might solve a long-standing puzzle: why some ancient gas clouds show remarkably uniform metal distributions while others contain bizarre, localized pockets of rare isotopes. The violent deaths of these stars weren't just in points, they were cosmic distribution centers, each methodically parceling out the ingredients for future stars, planets, and life in its own unique way. But here's the twist: the very existence of these explosions hinges on a delicate balance. If a star was too massive, it might have collapsed directly into a black hole without a supernova at all. Too small, and it would have died a relatively quiet death. That fine line suggests the first stars occupied a Goldilocks zone of destruction big enough to die spectacularly, but not so big that they left nothing behind. It's a reminder that even in chaos, the universe operates by invisible rules, and the echoes of those rule-bound cataclysms are woven into the atoms of everything around us, including you. The universe's first stars might be long gone, but their light could still linger stretched and faded into the cosmic infrared background, a faint glow permeating the entire sky. This isn't just random noise, it's a palimpsest of the cosmos's earliest chapters, and buried within it might be the spectral fingerprints of those primordial giants. Imagine trying to hear a single note in a symphony played at the edge of the universe. Every instrument is a galaxy, every chord is starlight, and the first stars are the faintest, most distant notes, barely audible beneath the roar of everything that came after. Mapping this infrared background is like decoding a cosmic hieroglyph. The light from those early stars has been redshifted so dramatically by the expansion of space that what once blazed in ultraviolet now whispers in infrared, with wavelengths stretched thousands of times longer than their original form. Telescopes like the James Webb and the upcoming SPHEREX mission are hunting for subtle anisotropies, tiny irregularities in this background glow that could betray the presence of ancient stellar clusters. The trick is distinguishing between the signatures of first stars and the infrared pollution from later galaxies, a task akin to picking out a single voice in a stadium crowd. One promising lead comes from the pattern of fluctuations. First stars didn't form uniformly, they ignited in patchwork bursts, leaving behind a specific statistical signature in the infrared background's texture. Simulations suggest their light should create a distinctive, clumping pattern, brighter knots where stars were dense, fading into darkness where the early universe still slumbered. Some researchers even speculate that the overlap of these primordial bubbles could produce interference like ripples, detectable as faint swirls in the infrared haze. But the real breakthrough might come from cross-referencing this data with other cosmic clues. For instance, regions of the infrared background that align with ancient gas clouds identified by their absorption of quasar light could pinpoint where first stars truly flickered to life. Other teams are correlating the background with gravitational lensing maps, hoping to spot distorted patches where the gravity of later galaxies magnified these first starlight echoes. It's detective work on a cosmic scale, piecing together fragments of a story written in light 13 billion years ago. The stakes are higher than just confirming a theory. If we can isolate these signals, they'd reveal not just when the first stars formed, but how, whether in isolation or in frenzied bursts, and how quickly they seeded the universe with heavy elements. Even more tantalizing, some theories suggest the infrared background could hide traces of population, 3 stars that didn't die in supernova but collapsed silently into black holes, their light snuffed out before it could fully join the cosmic chorus. Yet for all its promise, this hunt is fraught with false leads. Cosmic dust, distant galaxies too dim to resolve, even the thermal glow of interstellar objects in our own solar system, all can mimic the signals of first starlight. Disentangling the real from the noise requires algorithms sharper than any we've built, and instruments sensitive enough to detect temperature variations of a fraction of a degree across the entire sky. What keeps astronomers going is the sheer audacity of the quest. The cosmic infrared background isn't just a relic, it's the universe's oldest photographic negative, a snapshot of its first tentative steps out of darkness. And if we can finally develop the right tools to develop that image, we might witness something no human was ever meant to see, the dawn of light itself, frozen in the afterglow of time. For billions of years after the Big Bang, the universe was shrouded in a thick fog of neutral hydrogen, a cosmic twilight where light couldn't travel far without being absorbed. Then, suddenly, the fog lifted. Space became transparent, bathing everything in ultraviolet light. This monumental shift, called reionization, marked the universe's final transformation from darkness to light. But what exactly flipped the switch? For decades, astronomers assumed the first stars were the sole heroes of this story, their fierce radiation blasting electrons off hydrogen atoms in a process called ionization. Now, new discoveries suggest the plot might be far more complicated, with early galaxies and quasars possibly sharing the spotlight in this cosmic dawn drama. Consider the sheer scale of the challenge. To reionize the entire universe, you'd need an unimaginable number of ultraviolet photons, enough to strip electrons from every hydrogen atom across billions of light years. Population 3 stars certainly had the raw power. Their blistering surfaces emitted UV light 100 times more intense than modern stars. But here's the catch. These stars were also incredibly rare, scattered like distant campfires in an endless wilderness. Could their sparse light really have dismantled the cosmic fog so completely? Some simulations say no. Even with their extreme output, the first stars might have only carved out localized bubbles of ionized gas, like melting holes in a frozen lake, while vast regions remained shrouded in darkness. That's where galaxies and quasars enter the picture. While population 3 stars were flickering on, the first proto-galaxies were also assembling, packed with millions of younger stars. These stellar nurseries might have acted like cosmic floodlights, their combined UV output overwhelming nearby hydrogen faster than isolated stars could. Then there are quasars, supermassive black holes devouring gas and spearing the cosmos with jets of radiation so intense they could have reionized entire filaments of the cosmic web. Recent observations from the James Webb Space Telescope reveal quasars existing shockingly early, some just 700 million years after the Big Bang, right in the heart of the reionization era. The debate hinges on timing. If reionization happened rapidly, it points to a coordinated effort: stars, galaxies, and quasars working in concert. A slower, patchier process might mean population 3 stars did most of the heavy lifting before reinforcements arrived. Clues are buried in the cosmic microwave background, where subtle polarization patterns hint at how reionization unfolded. Some models suggest it began in isolated pockets before becoming universal, like a forest fire spreading until the whole horizon glows. Others argue the data shows a more synchronized event, as if someone flipped a galaxy-wide switch. What's at stake isn't just a technical detail, it's understanding how the universe became what it is today. If quasars and galaxies played starring roles, it means structures we associate with the mature cosmos were shaping events far earlier than we thought. But if the first stars truly did it alone, their significance grows even larger, not just as celestial pioneers, but as the architects of transparency, the entities that literally cleared the way for everything that followed. One thing's certain, the answer isn't either or. The universe rarely works in absolutes. Perhaps the truth lies in a messy, magnificent collaboration, a chorus of stars, galaxies, and black holes, each contributing their unique voice to the song that ended the cosmic dark ages. And as telescopes peer deeper into the infrared shadows of those early epochs, we might finally hear that song in full, revealing how light in all its forms won the war against darkness. Not every cosmic beginning has a happy ending. Some stars never got the chance to shine. Deep in the void, lurking between galaxies, could be the universe's greatest disappointments, vast, cold spheres of hydrogen that collapsed under gravity but never ignited. These failed stars, sometimes called dark hydrogen objects or black dwarfs in the making, represent a haunting what-if of cosmic history. Unlike their brilliant siblings, they're frozen in time, too massive to be planets yet too faint to be seen, silently drifting through space like ghosts of a future that never was. What doomed these would-be stars? The answer lies in a quirk of quantum physics. For nuclear fusion to ignite, a gas cloud needs to reach critical pressure and temperature at its core. But in the sparse early universe, some collapsing clouds may have lacked just enough mass or the right trigger. To cross that threshold, picture a car engine turning over but never starting, no matter how many times you crank the key. These objects stalled at the brink of stardom, their cores too cool to fuse hydrogen, leaving them suspended in a twilight state. Without the outward pressure of fusion to balance gravity's crush, they'd have continued shrinking until quantum forces finally halted their collapse, leaving behind bizarre, ultra-dense spheres no larger than Jupiter but hundreds of times heavier. The irony, these cosmic misfits might outlast every star that succeeded. While normal stars burn out in billions of years, a failed star could persist for trillions, its only heat coming from the slow leakage of primordial warmth trapped since its formation. Some theorists speculate that the universe's oldest failed stars could still be here today, cold, nearly invisible, and hiding in plain sight. Spotting them is a nightmare. Emitting no light and little infrared, their only giveaway would be subtle gravitational lensing effects as they pass in front of distant stars, warping starlight like a funhouse mirror for a split second. A handful of unexplained microlensing events in galactic surveys might already be hints of their presence, like footsteps of an intruder caught only on a motion sensor. But the real twist, these flops might have shaped the cosmos more than we think. A population of dark hydrogen objects could account for part of the infamous missing baryon problem, the puzzle of where a fraction of the universe's normal matter has gone. Their collective gravity might also subtly warp the orbits of visible stars at the edges of galaxies, potentially masquerading as dark matter in certain observations. And if they're more common than assumed, they could be the ultimate cosmic time capsules, preserving pockets of pristine Big Bang hydrogen in their cores, untouched by stellar nucleosynthesis. The lesson here isn't just about failure, it's about randomness. The same chaotic conditions that birthed thousand sun behemoths might have also created these inert shadows, proving that even in the universe's opening act, not every player was destined for glory. And if we ever do find one, it won't just be a curiosity. It'll be a window into the road not taken, a reminder that the night sky's brilliance rests on a knife's edge between ignition and eternal darkness. Quantum fluctuations, tiny, unpredictable ripples in the fabric of space-time, might have set the stage for the universe's very first stars. In the chaotic moments after the Big Bang, these subatomic tremors created microscopic variations in density, like invisible fingerprints pressed into the cosmos. At the time, these differences were unimaginably small, smaller than a single proton. But over billions of years, gravity amplified them, sculpting those faint wrinkles into vast cosmic mountains and valleys where gas pooled, cooled, and eventually ignited the fires of the first stars. Here's how it works. Imagine blowing up a balloon with tiny, random bumps on its surface. As you inflate it, those tiny imperfections stretch and grow, transforming into larger, more pronounced ridges. The early universe behaved similarly, expanding at a breakneck pace during cosmic inflation. Those quantum ripples were stretched across light years, becoming the seeds for all structure we see today. Regions with slightly more mass pulled in surrounding gas, while emptier patches stayed dark. Without these quantum fingerprints, the cosmos might have remained a featureless soup of hydrogen, eternally starless and still. But gravity didn't act alone. Dark matter, that mysterious, invisible substance, clung to these quantum-imprinted overdensities like cosmic scaffolding, accelerating the collapse of gas into star-forming pockets. Some simulations suggest that the first stars didn't ignite randomly, but at the intersections of these ancient quantum ripples where dark matter's pull was strongest. It's a staggering thought. The birthplaces of the universe's first lights might have been determined by fluctuations so small, they'd vanish in a flash if you tried to measure them directly. The echoes of these quantum seeds aren't lost to time. We see their legacy in the cosmic microwave background, the afterglow of the Big Bang, where temperature variations match the predicted patterns of those early density fluctuations. Even more telling, the distribution of galaxies today traces back to those primordial blueprints, like a galactic family tree rooted in quantum uncertainty. Yet mysteries remain. Why did some fluctuations grow into star-forming behemoths while others fizzled out? Could there have been exotic physics at play, extra dimensions, undiscovered particles that tweaked the rules? Some theorists speculate that certain ultra-dense regions might have birthed stars far earlier than we've observed, their light now redshifted beyond detection. Others wonder if alternate universes, born from different quantum dice rolls, ended up with entirely different stellar histories. What's certain is that the quantum origins of cosmic structure blur the line between the impossibly small and the astronomically vast. Those first stars didn't just light up the universe, they were the end result of a chain reaction that began with whispers in the void, proving that even the tiniest tremors can, given time, shake the foundations of reality itself. Cosmic strings, theoretical cracks in the fabric of space-time, could have been the universe's first sculptors, carving paths for starlight where none existed. Picture these hypothetical relics as unimaginably thin, infinitely dense threads left over from the Big Bang, vibrating with the energy of a singularity. If they existed, they wouldn't just hang idly in space. They'd whip through the cosmos at near light speed, trailing shockwaves powerful enough to squeeze diffuse gas into dense, star-forming knots. It's like dragging a needle through a cloud wherever the strings passed. They might have left behind trails of collapsing hydrogen, jump-starting stellar birth long before gravity alone could have done the job. Here's how the process could have worked. As a cosmic string sliced through a primordial gas cloud, its immense gravitational field would have yanked surrounding matter inward, compressing it violently along the string's path. The shockwave would have acted like a cosmic snowplow, piling hydrogen into ridges dense enough to collapse under their own weight. Unlike normal star formation, which relies on slow gravitational creep, this would have been a sudden, violent trigger, stars igniting like firecrackers along the string's trajectory. Some models suggest these strings could have created chains of stars, perfectly aligned like beads on an invisible wire, with masses far exceeding typical population 3 estimates. The most radical twist, cosmic strings wouldn't just compress gas, they might have heated it too. As they vibrated, they'd emit bursts of high-energy radiation, potentially ionizing nearby hydrogen and altering how quickly it could cool. This creates a paradox. While the shockwaves seeded star formation, the radiation might have delayed it in surrounding regions, creating a patchwork of brilliant stellar filaments separated by deserts of darkness. It's a double-edged sword, where the very mechanism that birthed stars could have also suppressed them elsewhere, explaining why some pockets of the early universe lit up while others lingered in shadow. Evidence for this wild idea is sparse but tantalizing. Astronomers have hunted for cosmic strings in the cosmic microwave background, where their passage should have left sharp, linear scars in the temperature patterns. So far, none have been definitively found, but absence of proof isn't proof of absence. Strings could be too faint, too rare, or oriented in ways that evade our telescopes. Others speculate that the peculiar alignment of certain ultra-distant quasars, their axes mysteriously synchronized across billions of light years, could hint at strings warping spacetime on cosmic scales. The implications stretch beyond stellar origins. If cosmic strings helped ignite the first stars, their remnants might still lurk in today's universe, their gravity subtly bending light from distant galaxies or distorting the timing of pulsar signals. Some theorists even suggest they could be the missing energy source behind unexplained high-energy cosmic rays particles zipping through space with velocities that defy conventional explanations. What's certain is this: if cosmic strings played midwife to the first stars, the universe's dawn was far stranger than we've dared imagine. Not a slow awakening, but a fireworks display orchestrated by invisible strings, a cosmic puppet show where the puppeteers were flaws in spacetime itself, and the puppets were the first fires to ever pierce the dark. What if gravity itself played by different rules in the early universe? While Einstein's theory of general relativity has been our cosmic rulebook for over a century, a handful of daring astrophysicists argue that tweaking gravity's laws might solve some of the biggest mysteries surrounding the first stars. Enter modified Newtonian dynamics, a controversial framework suggesting gravity behaves differently when pull becomes extremely faint, like in the sparsely populated voids of the primordial cosmos. If correct, this wouldn't just rewrite physics textbooks, it could radically alter our understanding of how and where those first stellar giants ignited. Under standard cosmology, dark matter's invisible pull is what gathered hydrogen into dense enough clumps to form stars. But Mann proposes an alternative. Instead of invoking unseen matter, gravity might simply strengthen when accelerations drop below a certain threshold. Picture a cosmic game of tug-of-war where the ropes behave unpredictably gentle pulls, suddenly gaining unexpected strength. In the early universe, where gas clouds were vast and diffuse, this tweak could have allowed gravity to compress isolated patches of hydrogen without dark matter's help, potentially forming stars earlier and in different configurations than conventional models predict. The implications ripple outward. Without dark matter halos directing traffic, MND suggests the first stars might have formed along vast, filamentary structures where gravity's modified effects were strongest, creating luminous tendrils weaving through space like glowing spider silk. Their distribution would have been less clustered than in traditional simulations, with fewer ultra-dense regions and more evenly spaced stellar pioneers. Some MND variants even predict stars forming in seemingly empty voids, places where standard physics insists there wasn't enough mass to trigger collapse. Yet challenges remain. MND struggles to explain certain large-scale observations like the bullet cluster's gravitational lensing without some form of invisible mass. And critics point out that even if modified gravity jump-started star formation, it's unclear how it would account for the staggering energy outputs of population 3 stars. Their ultra-bright UV radiation seems to demand the extreme densities only possible with dark matter's compressive might. Still, a handful of tantalizing clues keep the theory alive. The James Webb Space Telescope's discovery of surprisingly mature galaxies in the universe's infancy has some researchers wondering if MND-like effects could have accelerated structure formation just enough to bridge the gap between theory and observation. The debate isn't just academic, it cuts to the heart of how we interpret the cosmic dawn. If MND or another alternative gravity model gained traction, we'd need to revisit everything from the timing of reionization to the chemical signatures of ancient stars. It's a reminder that the universe's first light might not just illuminate stellar origins, but also reveal whether we've fundamentally misunderstood the force that shaped them. Until then, these alternate gravity theories stand as thrilling provocations, challenging us to consider whether the rules we take as gospel might be far more flexible and far stranger than we ever imagined. The idea that some of the universe's first stars might still be burning hidden in quiet, forgotten corners sounds like pure fantasy, yet the possibility isn't as far-fetched as it seems. Most population 3 stars lived fast and died young, but what if a few escaped the usual fate? Imagine a cosmic Methuselah, a relic from the dawn of time, quietly simmering in some lonely pocket of space while galaxies rise and fall around it. The key lies in mass. While the largest stars burned out in mere millions of years, smaller ones, those at the lower end of the population 3 spectrum, could have survived for billions. If a handful formed with only 20 or 30 times the mass of our Sun, their slower fusion rates might have granted them lifespans stretching into the modern era. But where would they hide? The early universe was far less crowded, meaning some stars could have been flung into the void during chaotic gravitational interactions, left to drift in the emptiness between galaxies. These cosmic castaways, untouched by later generations of star formation, might still linger in regions where the gas is too thin to form new stars, making them nearly invisible against the blackness of intergalactic space. Their light, stretched by cosmic expansion, would be faint and redshifted into near undetectability, like a whisper drowned out by the roar of modern galaxies. Detecting such a survivor would demand a perfect alignment of technology and luck. The James Webb Space Telescope offers our best shot, its infrared sensitivity tuned to catch the dim, ancient glow of these relics. Astronomers would search for stars with bizarre chemical signatures, almost no metals, yet somehow shining in isolation. Even more telling would be their motion. Unlike modern stars which orbit galactic centers, a population 3 survivor would likely drift aimlessly, its trajectory a dead giveaway of its primordial origins. The real challenge, confirming it's not just an oddball second-generation star. Some ultra-metal poor stars in our own galaxy, like SMSS J03-1300, 36-670,839. 3 come close, but none are perfect zeros. A true first-gen survivor would have no detectable carbon, oxygen, or iron, its composition untouched by supernova debris. Even then, skeptics argue that turbulence in the early universe should have prevented the formation of many long-lived population 3 stars, leaving the odds of a living relic vanishingly small. Yet the hunt is irresistible. Finding one would be like stumbling upon a living dinosaur, proof of an era we thought lost forever. It wouldn't just rewrite stellar evolution, it would hand us a time capsule from the cosmic dark ages, letting us study the universe's first light as if it never went out. And if we ever do spot one, it'll raise a thrilling question. How many more are out there, hiding in plain sight, waiting to be found? For decades, astronomers painted the universe's first stars as colossal behemoths, monsters hundreds of times heavier than our sun, burning brilliantly and dying young. But what if that's only half the story? Emerging simulations now suggest a radical twist. Some of these ancient stars might have been surprisingly petite, barely tipping the scales at 10 or 20 solar masses. These cosmic underdogs wouldn't just rewrite the narrative of stellar evolution, they could still be out there, hidden in plain sight, quietly outliving their giant siblings by billions of years. The key lies in turbulence. While the early universe was indeed a hotbed for forming massive stars, it wasn't a uniform factory line. Chaotic gas flows, shockwaves from dark matter interactions, and magnetic fields could have fractured collapsing clouds into smaller fragments, like a glass shattering into both large and tiny pieces. Some of these fragments might have been dense enough to ignite fusion, but too small to grow into titans. Picture a cosmic Goldilocks zone, not too massive to burn out quickly, not too small to fizzle as failed stars, just right for endurance. These lightweight population 3 stars would have burned cooler and dimmer, their lifespan stretching into tens of billions of years rather than mere millions. The implications are staggering. If even a fraction of first-gen stars were sun-sized, they could have seeded the cosmos with metals at a steadier pace, avoiding the violent boom and bust cycles of their giant cousins. Their supernova, though less energetic, would have distributed elements like carbon and oxygen more evenly, potentially smoothing out the patchy chemical enrichment we see in ancient gas clouds. Some models even suggest these stars could have acted as anchors, their gentle gravitational pull helping to stabilize early protogalaxies that might otherwise have been ripped apart by the explosive deaths of larger neighbors. But why haven't we spotted them? Their longevity is ironically their cloak. While massive population 3 stars died in fireworks visible across the universe, these smaller survivors would have faded into the background, their light drowned out by younger, brighter stars. Their telltale signature, a near-total lack of metals, is also a double-edged sword. Modern telescopes struggle to distinguish them from second-generation stars with slightly polluted atmospheres. It's like trying to find a single unmarked white thread in a tapestry woven with similar shades. The hunt is far from hopeless, though. Astronomers are refining techniques to detect these relics by their subtle vibrations. Smaller stars oscillate differently than larger ones, their interiors vibrating at distinct frequencies like instruments in an orchestra. Space observatories like Pluto, designed to study stellar oscillations, might finally tease out these ancient whispers. Others are scouring the Milky Way's halo for stars with bizarrely low angular momentum, a potential clue they formed before the galaxy's rotation fully developed. The most tantalizing possibility, some of these primordial suns might still be burning in our cosmic backyard. If one drifted close enough, its light could betray its age through missing spectral lines. No iron, no silicon, just the barest whispers of hydrogen and helium. Finding even a single survivor would rewrite stellar archaeology, offering a direct window into the universe's first stellar recipe. This theory doesn't just challenge assumptions, it reveals a cosmos more nuanced than we imagined. The dawn of light wasn't just a story of giants, it was a tapestry woven with threads of all sizes, each playing a role in shaping the universe we see today. And if the models hold, the night sky might still hold ancient embers from that first cosmic fire, waiting to be recognized. The universe's first stars might owe their existence to particles we've never even detected. Among the most tantalizing possibilities are Action's hypothetical, ghostly particles originally proposed to solve a quantum physics puzzle, but now suspected of playing a far grander cosmic role. If they exist, these elusive entities could have supercharged the cooling of primordial gas, fundamentally altering how and when the first stars ignited. Picture this: in a universe without heavy elements, hydrogen relied on molecular hydrogen 2-bound atoms to shed heat and collapse into stars, but that process was painfully slow, like trying to chill a boiling pot with nothing but a whisper. Actions streaming through space in unimaginable numbers might have provided an invisible escape route for that heat, cranking the universe's thermostat down faster than gravity could keep up. Unlike normal particles, actions barely interact with matter. They're more like cosmic neutrinos turned up to 11, but their sheer abundance in the early universe could have made them game changers. As hydrogen gas swirled in protostellar clouds, actions produced inside, spawned by the intense heat and magnetic fields, might have carried energy away with unmatched efficiency. Think of them as microscopic heat vampires, draining thermal energy directly from the gas and accelerating its collapse. Some models suggest this exotic cooling could have compressed gas clouds 10 times faster than standard physics predicts, birthing stars not just earlier, but in wildly different sizes and configurations. Instead of the usual suspects, colossal, short-lived giants, we might have gotten a mix of strange stellar oddities, ultra-dense middleweights, or even flickering, low-mass stars that defied the era's expectations. The wildest part, this wouldn't just tweak stellar formation, it could solve cosmic mysteries. Astronomers have long puzzled over why some ancient star clusters appear chemically too mature for their age, as if they formed under conditions we can't replicate in simulations. Action cooling might explain it. If gas could chill rapidly enough, stars might have formed from smaller, denser clumps, enriching their surroundings with metals sooner than expected. Even more provocatively, these particles could account for anomalies in the cosmic microwave background, those faint temperature ripples that shouldn't align with current models if actions were silently siphoning heat 13 billion years ago. Skeptics, of course, demand proof. Actions remain theoretical, and alternative explanations like turbulence or magnetic fields could mimic their cooling effects. But the hunt is on. Laboratories deep underground are racing to catch an action in the act, using powerful magnetic fields to coax them into revealing signals. Meanwhile, astrophysicists scour ancient stellar spectra for anomalies, unexpected ratios of isotopes, or bizarrely uniform temperatures that might betray action involvement. Even gravitational wave detectors could stumble onto clues. If actions altered star formation, the mass distribution of merging black holes might carry their fingerprint. What's at stake isn't just another particle for the physics zoo. If actions shaped the first stars, they'd bridge the quantum and cosmic scales, proving that phenomena we can't yet see orchestrated the universe's earliest light. And if we confirm their role, it'll mean the cosmos didn't just unfold under the laws we know. It danced to the tune of particles so strange they redefine what's possible. Until then, actions remain both a tantalizing solution and a reminder. Sometimes the universe's greatest architects are the ones hiding in plain sight. What if the universe's first stars weren't entirely ours? If the multiverse theory holds that our cosmos is just one bubble among countless others, then the earliest moments of existence might have been messier than we imagined. Picture neighboring universes brushing against our own in the chaotic aftermath of the Big Bang, leaking traces of their physics into our nascent reality. These cosmic transfers could have left behind exotic particles, altered fundamental constants, or even seeded pockets of unfamiliar chemistry where the first stars ignited. The result, stellar oddities with compositions that defy every model based solely on our universe's rules. Take the mystery of primordial lithium. The Big Bang produced precise amounts of hydrogen, helium, and a smidge of lithium. But when we examine the oldest stars, some show lithium levels far lower than predicted. One possible explanation: contamination from a universe where weak nuclear force operates slightly differently, altering how nuclei fused in those early moments. Or consider stars with bizarre isotopic ratios, like too much helium-3 or carbon-13, which some physicists argue could be fingerprints of foreign physics smuggled in during cosmic inflation. These anomalies might not just be random noise, they could be clues that our first stars were cosmic hybrids, forged in a reality that wasn't entirely isolated. The mechanism behind this cross-universe pollution is as wild as the idea itself: quantum tunneling. The same phenomenon that lets particles teleport through barriers might have allowed energy or matter to bubble hop during the universe's hyper-expansion phase. Think of it like soap bubbles colliding in a sink. Where they touched, a brief bridge could have formed, permitting exchanges before the universes pinched off and drifted apart. Even a few stray atoms transferred this way could have had cascading effects. If a single carbon nucleus from a universe with stronger nuclear forces slipped into a collapsing gas cloud here, it might have jump-started cooling faster than pure hydrogen could, birthing stars earlier or stranger than expected. The implications spiral outward. If multiverse contamination occurred, it could explain why some population 3 stars seem to have formed too early in certain regions, as if an outside hand tipped the scales. It might also account for the perplexing uniformity of certain elements across vast distances, like cosmic seasoning sprinkled evenly through the primordial soup. Skeptics, of course, argue these anomalies have terrestrial explanations: telescope calibration errors, or our incomplete understanding of nucleosynthesis. But the tantalizing possibility remains that we're reading someone else's recipe in our oldest stellar fossils. Detecting proof would require instruments sensitive enough to spot statistical deviations in the cosmic microwave background's polarization patterns, subtle swirls that could betray ancient collisions with other universes. Others propose hunting for stars with impossible nuclear decay rates or elements that shouldn't exist under our laws of physics. It's a needle in a haystack search, but the payoff would rewrite cosmology. Confirming multiverse contamination wouldn't just reshape our understanding of the first stars, it'd prove we're living in a far more crowded and interconnected reality than we ever dreamed. Until then, these theories remind us that the universe's earliest light might hold secrets not just from our past, but from realities beyond our own. Gamma ray bursts, the most violent explosions in the universe, might be the final screams of the first stars echoing across time. These beams of pure energy, capable of outshining entire galaxies for a few blinding seconds, have long puzzled astronomers. But recent research suggests a startling connection. The deaths of certain population 3 stars could have birthed a special class of ultra-powerful gamma-ray bursts, acting as cosmic beacons from the dawn of time. When the most massive first stars collapsed, some didn't just explode, they may have formed rapidly spinning black holes, their immense gravity twisting surrounding gas into a swirling disk. As matter spiraled inward at near light speed, it could have funneled into twin jets of plasma piercing through the dying star like a cosmic blowtorch. These jets, packed with gamma rays and charged particles, would have shot out into space in tight beams. If one happened to point toward Earth billions of years later, we'd witness it as a short gamma ray burst, an impossibly bright flash that vanishes almost as quickly as it appears. What makes these events special isn't just their power, but their fingerprints. Unlike modern gamma-ray bursts, which often carry traces of heavier elements, a population 3-powered burst would leave a clean chemical signature, mostly helium and hydrogen, with almost no metals. It's like comparing the smoke from burning fresh wood to that of plastic. The composition tells you what fueled the fire. Telescopes like the upcoming Cherenkov telescope array are being fine-tuned to spot these telltale signs in the afterglow of distant bursts, hunting for the pristine chemistry that could betray a first-gen star's demise. The timing adds another clue. Gamma-ray bursts from the earliest epochs of the universe would be stretched by cosmic expansion, their light redshifted into longer wavelengths. Some of the most distant bursts ever detected, like GRB 090429b, originating just 600 million years after the Big Bang, show spectra so skewed toward infrared that they almost slipped past our detectors. These ultra-redshifted bursts could be the smoking guns linking gamma-ray explosions to population 3 stars, especially if their host galaxies or lack thereof match predictions for the sparse early cosmos. But here's where it gets speculative. A few theorists propose that the rarest, most energetic gamma-ray bursts, the ones lasting mere milliseconds, might be the remnants of collapsar stars, first-generation behemoths so massive they skipped the supernova stage entirely, imploding directly into black holes with a gamma-ray scream. These events would have been far brighter than anything we see today, potentially visible across the entire observable universe. If we could catch one in the act, it would offer a front-row seat to the death throes of a true cosmic titan. The implications stretch beyond mere astrophysics. Gamma-ray bursts from the first stars might have played a role in reionization, their intense radiation helping strip electrons from hydrogen atoms and clear the cosmic fog. They could also explain mysterious gaps in the distribution of ancient gas clouds. A nearby burst would have sterilized vast regions of space, delaying star formation for eons. Even more intriguing, the heavy elements forged in these explosions might have been catapulted across intergalactic space by the jets, seeding future stars with metals in patterns we're only beginning to decode. Yet for all their potential, these bursts remain elusive ghosts. Detecting them requires perfect timing and luck, catching a flash that might last less than a second, from an era when the universe was a fraction of its current size. New observatories like the Vera Rubin Observatory, with its ability to scan the entire sky every few nights, could tip the odds in our favor. Others are developing algorithms to sift through archival data, searching for mist bursts that might have been dismissed as noise. The hunt isn't just about solving a cosmic mystery, it's about turning catastrophe into opportunity. These explosions, though devastating, act like flashbulbs illuminating the darkest corners of time. By studying their afterglows, we might finally glimpse the shadows of the stars that lit the universe, proving that even in death they still have stories to tell. Deep in the cosmic static, there's a whisper waiting to be heard, a faint radio signal from hydrogen atoms that could rewrite the story of the universe's first starlight. This whisper, known as the 21-centimeter line, is the fingerprint of neutral hydrogen, and it carries secrets from an era before galaxies, before planets, before even the first stars had fully awakened. When astronomers finally decode this signal, it won't just tell us when those primordial giants flickered on, it'll map their exact locations across the sky, painting a portrait of cosmic dawn in strokes of radio waves. Here's how it works. Hydrogen, the universe's most abundant element, has a quirk. The proton and electron in each atom can exist in one of two quantum states, aligned or anti-aligned, and flipping between them releases or absorbs a photon with a wavelength of 21 centimeters. In the cold, dark early universe before stars lit up the cosmos, these hydrogen atoms were bathed in the afterglow of the Big Bang, humming at this exact frequency. But when the first stars ignited, their ultraviolet radiation blasted through the darkness, exciting the surrounding hydrogen and altering how it absorbed 21-centimeter photons. These interactions left scars in the signal's intensity, like shadows cast by starlight we can no longer see. The magic lies in the details. By measuring subtle dips and spikes in the 21-centimeter line at different redshifts, astronomers can reconstruct a three-dimensional map of where and when stars first formed. A sudden drop in signal strength might mark the moment a cluster of stars ionized their surroundings, while a lingering spike could reveal a stubborn pocket of darkness where starlight hadn't yet reached. It's like turning static into a time lapse, watching the universe flicker awake, one star at a time. But capturing this signal isn't easy. Billions of years of cosmic expansion have stretched those original 21-centimeter photons into meter-long radio waves, which now arrive at Earth drowned out by everything from cell phones to galactic synchrotron radiation. Projects like the Square Kilometre Array and the Hydrogen Epoch of Reionization Array are racing to filter out the noise using supercomputers and custom algorithms, isolating the primordial whispers from the modern cacophony. The payoff: a revolution in our understanding of cosmic dawn. If the 21-centimeter signal matches predictions, it'll confirm that stars formed in isolated, massive clusters. If it deviates, we might need to rethink dark matter's role or consider exotic physics like decaying neutrinos warping the timeline. There's even a chance we'll catch echoes of secondary effects like the X-rays from early black holes heating hydrogen in ways stars alone couldn't. This isn't just about filling in a textbook timeline. The 21-centimeter line is a bridge between theory and observation, a chance to test decades of simulations against the universe's own records. And if we're listening closely enough, it might even reveal surprises like stars flaring up earlier than we thought, or vanishing entirely in regions where dark matter clumped too densely. The cosmos keeps its secrets written in radio waves, and we're finally tuning in. Supercomputer simulations have become the ultimate time machines, letting us rewind the cosmos to witness the birth of the first stars in digital recreations. Projects like Illustris TNG and Eagle don't just guess at how those primordial giants formed, they brute force the problem, simulating billions of particles governed by the laws of physics to see what emerges. The results are staggering: virtual universes where stars flicker to life in sprawling filaments of gas, where supernovae seed space with metals, and where black holes grow from seeds to monsters. These cosmic laboratories have reshaped our understanding of population 3 stars, revealing formations so violent and chaotic they defy textbook explanations. Yet for all their power, simulations hit walls. Take the mystery of cosmic variance, why some regions of the early universe light up with stars while others stay dark. Models can't yet reconcile the patchiness we observe in quasar light with the smoother distributions their equations predict. One running theory blames turbulence, those chaotic swirls in primordial gas that might have fragmented star-forming clouds unpredictably. Another points to magnetic fields too faint to detect but strong enough to steer collapsing gas like invisible rails. The most haunting gap: no simulation has recreated the full spectrum of ancient stellar masses we infer from chemical traces. They either produce too many monsters or too few middleweights, missing the Goldilocks zone where reality seems to reside. The stakes aren't just academic. Every mismatch between simulated starlight and observed data hints at physics we've overlooked, perhaps exotic dark matter interactions or quantum effects scaling up in ways we never anticipated. Some teams are now grafting speculative ideas onto their code, testing whether action like particles or primordial black holes could bridge the gaps. Others are crowdsourcing solutions like the Sphinx project, which lets astronomers globally tweak variables in real-time collaborations. What's emerging is humbling. The first stars didn't form in a vacuum, but in a universe buzzing with invisible actors and untested rules. Until simulations can mirror the quirks of ancient starlight perfectly, we're left with a tantalizing duality, theories polished by supercomputers, yet still scratching at something deeper, wilder, and just out of reach. The ultimate test, when a simulation not only predicts the past but discovers something new about it, like a virtual universe whispering secrets we've yet to uncover in the real one. Even after centuries of study, the universe's first stars remain one of astrophysics' greatest puzzles, but also its most thrilling frontier. From dark stars lurking in the shadows to quasi-stars with black hole hearts, from cosmic strings carving paths for starlight to actions cooling primordial gas in ways we're only beginning to understand, every theory we've explored is a testament to human curiosity's boundless creativity. Some ideas feel almost mythic, like the notion that sterile neutrinos or primordial black holes, particles and objects we've never directly seen, might have midwifed the cosmos's first light. Others, like the haunting possibility of a surviving population, three-star drifting undetected in the void, blur the line between science and cosmic poetry. What ties these theories together isn't just their audacity, it's their stakes. Unraveling how the first stars formed isn't just about rewriting textbooks, it's about tracing our own origins. Every atom in our bodies, every planet, every galaxy owes its existence to those primordial giants. Their deaths forged the elements that built us, their light ended the cosmic dark ages, and their remnants might still shape the universe today in ways we're only starting to glimpse. This is where the James Webb Space Telescope becomes our time machine, with its infrared eyes peering deeper into the past than any instrument before. JWST is already turning hypotheses into data. Those puzzling early galaxies it's discovered too massive, too bright, too soon might be the grandchildren of population 3 stars, their odd chemistry a clue to what came before. Future telescopes like the Nancy Grace Roman Space Telescope or ground-based behemoths like the Extremely Large Telescope will push further, hunting for the direct fingerprints of first starlight in the cosmic infrared background or isolating 21-centimeter signals from the dawn of time. But the most exciting answers might come from surprises, anomalies no theory predicted, like a star with 0 metals or a gamma ray burst from a collision we didn't think was possible. That's the beauty of cosmic detective work. Every mystery solved unveils 2 more, and the universe always keeps a few wild cards up its sleeve. So now it's your turn. Which theory feels most compelling? Do you think dark matter sculpted the first stars, or was it cosmic strings weaving light into the void? Could actions have secretly shaped stellar birth, or are we missing an even bigger picture? Drop your thoughts in the comments, because the story of Cosmic Dawn isn't just for astronomers. It's a saga written in starlight, and we're all part of what comes next.